Okay, I'm going to go ahead and describe these codes in this file, 10.10.17 continued, the new codes. And I'm not going to give a code outline, but hopefully you can, based on this description, make some progress on writing this code. Okay. So, first of all, you should modify your code in 4D into a function called cutoff fun with these inputs, which you recognize already, that outputs the cutoff based on these given parameters. So what you're going to do is go to this Bernoulli code outline. You see here that this part of the code generated your cutoff value. So you'll just be taking this part of the code, extracting it, and making it into a function. And then you should put that together with your other functions in this Bernoulli funds.py. Now, you can do that simply by clicking into Bernoulli funds.py and editing it just as if it was a notebook. All right? So that should be pretty straightforward. Now, here's the new code. This code is to evaluate cutoff for different numbers of trials and store the results in a vector. The cutoff that we found here is only for big N trials. So I want to find cutoffs for any number of trials up to big N. So if you have fewer than N trials, you'll still have a cutoff, but it won't be the same number. Okay, this way we can evaluate an ongoing detection process. What we're going to do is use this detection process as we go. So after 30 trials, we do the detection. After 31 trials, 32 trials, and so on. We don't just wait until 100 trials and do one detection. We do detection as we go. Right, so in order to evaluate the cutoffs for different numbers of trials, we'll do a for loop that goes from D to N. We don't do less than D because you need at least D trials to make some kind of evaluation. Now, for each value of N, use your code cutoff fun that you just made here. I should say, instead of code, says use, so you can, instead of saying use your code, I should say call your function. Right, you're going to call cutoff fun to evaluate the cutoff corresponding to this value of N. In other words, you're going to replace big N with little n in the function call. And you should store these results in a vector cutoff vector. And so you'll use the other values as we used previously. All right, and then this code is going to make use of this cutoff vec to evaluate the effectiveness of the detection as the number of trials increases. So in this code, we'll make the probability go bad after the 25th trial. We want to see how long it takes the algorithm to detect the error. All right. So first you'll use bgenfun to generate your matrix. Then you'll do a for loop that goes from D to big N. And use D equals 6. So I'm going to use blogfun to create vector of log probabilities. Okay, let's see. Go down here. Actually, I don't think I'm not even sure I want to do that. Let me think for a second. Yes, that's right. That's actually what I want to do. I'm getting the probability results for N trials at a time, and I'm going to be storing that in a matrix, and I'll call it log prob mx. So instead of a log probability vector, I'm going to have a log probability matrix. And you want to go through the rows of log probability matrix and find the index of the first column in which the value exceeds the corresponding value of cutoff x. So what you're going to do is, like in the first row, you look through and you see where is the first column where the value in the row exceeds the corresponding value of cutoff vec. Now, cutoff vec depends on the column index, right? There's a cutoff vec for D plus 1, and so on. So you're comparing the nth column, or the little nth column, versus the little nth entry of cutoff vec. So each column is compared to the corresponding value in this cutoff vector. And we want to create a new vector detect with these indices. So this vector detect is going to have integers, and it's going to tell you how many trials it took before the detection took place. And then I want a histogram of this vector detect. All right? So try to get as far with this as you can. I'll be giving additional explanations, and we'll see where we can get with that.